Okay, welcome back, everybody. This is going to be our first example for projectile motion or 2D kinematics, and depending on how long this takes, I may even squeeze a second one in here as well. But this first one is going to deal with a skateboarder, and the skateboarder is going to be dropping a ball. All right, and so let me see if I can draw kind of a stick skateboarder. All right, so here he is, and so there's our wheels right there, and he's got this, and he's holding the ball out like that. Okay, and so the ball will make it red. Okay. So why is it a skateboarder? Why isn't it just a regular person standing right there? Well, the assumption is that the skateboarder is moving. He's rolling in the horizontal direction. Okay, and that horizontal direction, that constant speed, is 1.30 meters per second. And so what that means is that's going to be the initial velocity of the ball as it is released. Okay, since the whole skateboarder system is moving at 1.30 meters per second, and that means that's going to be the velocity of the ball when it is dropped. All right. So initial velocity is going to be 1.30 meters per second. Okay. I hope I see a little typo right here. Releases the ball from a height. It should be from a height of 1.25 meters above the ground. All right, so let's make sure we include the ground right here. I'm going to make that gray. There we go. Okay, and so it was 1.25 meters above the ground. So that means the initial position in the y direction, 1.25 meters above the ground. So that's going to be our y initial right there. So y initial equals 1.25 meters above the ground. All right. We're also going to assume that this position right, let's see if I can draw a little kind of tick mark on the ground right here. This mark, that tick mark right below where the ball is, that's going to be x initial, and we're going to call that 0. Now the problem, as it is stated, calls it xo, okay, for original. Well, wherever we see xo, we call that x initial, and yo, we call that y initial, kind of like I did right here, 1.25, right? So that means the same thing. It's just a different notation. So what we want to do is we want to find x, I should really say x final, right there, kind of how I wrote it in right there, and y final. I like being specific. Oops, there's a y there already. I like being specific and saying x final and y final after a certain period of time right there. So that's what we want to find. We want to find x final and y final for two different periods of time, 0.250 seconds and 0.5 seconds. So the way to do this is to set up a table, all right, a table that has the x and the y directions represented. All right, so I'm just going to do x right here, and I'm going to do y right. Just give it some space right over there, and the table is just going to be like a regular old T that looks like this. Okay, and we're going to see how our x and our y directions. We'll see what we have first of all, and then we will we'll see what the final position and velocities of the x and y direction are. All right. So, what is the x initial? The initial x position. X initial equals 0 meters. The object is starting at some point 0. All right, what is the y initial position? Y initial, erase that there, equals 1.25 meters. 1.25 meters. We want to find the x final. That's one of our question marks. And we want to find the y final. Y final equals question mark. So if we know what the delta y is, we could solve for that final right there. But the relationship between the initial and final is that delta y, or the delta x. All right, let's write down what else we know. The initial velocity in the x direction, in the x, equals 1.30 meters per second, right? Because the skateboarder is rolling at 1.30 meters per second, and he's holding the ball. We know that the acceleration in the x direction is 0, right? So if you really want to write that, acceleration x direction equals 0, which means that the final velocity in the x direction is going to be the same thing as the initial velocity, which is going to be 1.30. In fact, I'm just going to erase that for the sake of space. So we're going to say the final velocity in the x direction is 1.30 meters per second as well. All right, and the one thing that is the same between x and y is time. So I'm just going to put t equals our first time. That's 0.250 seconds. All right, and that's going to be the same thing as our time in the y direction. Because I said this in the previous segment. But the only thing that links x and y together is going to be time. So 0.250 seconds. That's the common thread, you might say, because otherwise these two axes are entirely independent of each other. Okay? Well, what else do we have going on in the y direction? Well, we know the acceleration in the y, right? That is negative 9.81 meters per second squared. And we also know the initial velocity in the y direction. Initial velocity in the y is what? Well, if it's moving entirely horizontally, there is no y component, so we can say that that initial velocity in the y direction is 0 meters per second. All right. So, what else do we need? Or what else do we need to write in there? I think we have everything. All right. So this is how I usually set it up. I make an x column and a y column, and I just start writing down everything I know for x and everything I know for y. So, let's see if we can find the final x position, given the initial x position, the initial velocity, the final velocity, and time. All right. Well, what is the equation that that links position and initial velocity and final velocity and time in the x direction? Well, in the x direction, we'll write this for x final at 0.250 seconds. All right, we can say displacement delta x equals initial velocity in the x direction times time. And then if we want to keep going, we can say plus 1/2 at squared, right? But wait a minute, there is no acceleration in the a direction, so we can just stop right there. All right. So this is one of our kinematics equations. I'm used to writing as delta x right there. If we want to write this as x initial and x final, it would look like this. X final minus x initial equals initial velocity in the x direction times time. Okay? So let's find that final position. What are we going to do? We're going to take this x initial and we're going to add it over. All right? So well, wait a minute. What is that x initial? That's 0 anyway, right? That would be silly to do that. So we're just going to take that and cross that out. So our final x position is going to be initial velocity in the x direction times time. So that's going to be 1.3 meters per second. I should put the 1.30. 1.30 meters per second times, how much time has elapsed? 0.250 seconds. All right, and so our final x position, I should really put xf at 0.250, right, because we've got to be specific right there because there's different times involved, is going to be the product of those two values. Simply multiply together. So what is that? What is 1.30 times 0.25? So I feel like I should be able to do that in my head, but it's late, and so times 0.25. 0.325. All right? 0.325 5. And so x final right here, x final at 0.25 seconds is, that distance is 0.325 meters. Okay, I should put a meters right there. So that's our x final at 0.250. Okay, let's find our final position at y now. Okay, for x final at 0.250 seconds. Oh, that's funny. I meant to put y final, but I said x. It wound up looking kind of like a y anyway. This is y, right? For y final. Our final position in the y direction at 0.250 seconds. Well, what do we have here? We have the initial y position. We're solving for the y final, okay? We have the acceleration in the y. We have the initial velocity in the y direction, right? Because it's not moving. Look at this right here. It's not moving in the vertical at all. It's moving only in the horizontal. So initial velocity in the y direction has to be 0. But we do know the time. That time is 0.250 seconds. So we can use that same equation that we used for the x value, just a longer version of it because we have to deal with acceleration now. Okay? So delta y equals initial velocity in the y direction times time, plus 1/2 acceleration in the y direction times time squared. All right, this is the equation that we're used to using. Of course, the delta y can be broken into y final minus y initial, equals VIY times time plus 1/2 acceleration time in the y times time squared. All right, we're going to solve just for that y final, so we're going to add that y initial over to this side. All right, so I'm running out of space here a little bit. Y final, here's going to be a working equation for y final. Wait, again, let me be more specific again. For y final at what time? At 0.250 seconds is going to be y initial plus initial velocity in the y direction times time plus 1/2 acceleration in the y direction, which of course we all know, that's gravity, times time squared. All right, so that's going to be equal to, what's our y initial? 1.25 plus initial velocity in the y direction. Well, that's going to go away, right? Initial velocity in the y direction. What is that right there? That's 0, right? So that means this whole part, that's going to go away. It won't always, but it will in this part because there's 0 initial velocity in the y direction. And then we have to add our plus 1/2 at squared. 1/2 x. So what's our acceleration in the? Instead of writing 1/2, I'm going to write in 0.5 plus 0.5. That's our 1/2 right here. All right, times negative 9.81 times our time squared. What's our time? Time is 0.250 squared. All right, and that's going to give us our final y position of this ball. All right, 1.25 plus 0.5 times negative 9.81 times the quantity 0.250 squared. And that gives us 0.94 meters. And that's our final y position right there. All right, so it started at 1.3 meters, but after a certain amount of time has elapsed, it has dropped down to, I don't know, we'll call that right about there, 0.94 meters. So that is our, that's our y final. Okay, so what has happened right here to this ball? Well, it has moved in the horizontal to the tune of, 0.35 meters. But it's also moved downwards as well. It's moved downwards, what is 1.3 minus 0.94? That's like 0.36, right? 0.36 meters. So it has moved downwards kind of like that to that point right there. That's only after a quarter of a second, 0.250 seconds. All right, but as we're going to see as we continue this example in the next video, this ball is going to keep moving horizontally and keep moving negatively as it kind of follows this trajectory down towards the ground. Because again, the skateboarder isn't throwing it forward, but it's just kind of rolling forward with it. He releases it, and the ball takes a path that has an X component and a Y component. Okay? So, I think what I'm going to do for the next segment is I'm going to skip part B, all right? Because we did part A. We found the time for X final and Y final at part A right here. But we want to find the velocity, the speed, and direction of the motion of the ball at time equals 0.5 seconds. That is 1/2 second after the ball is released from the skateboarder. All right, and that's going to involve some of our knowledge of trig and of vectors, but I think it'll come back to you. All right, so thank you for bearing with me and following along. We're going to continue example 4.1 in the next video by doing just part C right here, and that's going to be finding the velocity of the ball at t equals 5 seconds. Thanks for following along. I'll see you on the next one.